Hello, Katarina. Hello, friends. Hey, Serena, Frank.
Hello. Hi.
Great to see you all again.
Hey, sorry, I was putting the topics up.
Thank you. They look beautiful.
How are you? Is that good? There's no chemistry topic, so to choose
I
from.
know. I still I haven't made that suggestion, Jamie's suggestion, that we are able to choose our own. Hey, Jamie.
I feel discriminated against.
Oh, I didn't say hi to you.
As a chemist.
No, there's no chemistry topic.
Yeah.
I know, right? That's unbelievable. How is there no?
How did they leave out the chemists?
I don't know.
Strange. Maybe somebody had a bad experience. It's no excuse.
It's funny that, when you, as a TA in grad school, when you TA organic lab and organic chemistry, it's mostly pre-meds that are required to take the course and they hate it with a passion. But they're determined to get their A and they want, it's hilarious.
Good evening, Serena, Victoria, Katerina, all of Science Society. Hello.
Hi, Jamie. Hi, Brett.
Jamie.
Welcome.
Hey, Brett.
Thank you for coming. Let
Hey,
me
how's
make
it going?
moderator so you can share your link.
Perfect.
We practiced this.
Now I just have to get the actual link. Hold on.
If you'd like to have a photo instead of your initials, you can also do that. Or if you have any, let's see, molecular photo idea.
Brett has a link where you can find both the text of the presentation and then also a link to the figures, both. And this is really great that Brett did that because it's really more accessible for
Yeah,
Jamie.
thank you very much. Well, I mean, other people like me too, not just me.
No, not
But-
just you, but
Sure, yeah.
thank you.
Thank you very much.
So we can learn from that in case you want to learn from that. If you click on the link, you see the slides, and then there's a link to the PDF slides, which are better if you would like to have a visual input. But if you don't, or if you cannot use a visual input, you can, have an app reading all the text, for example, to you, or follow along with the text if that's more helpful for you. It's really cool. Thank you, Brett.
Yes, thank you. I'm glad you mentioned that also. I have a tendency to skim right over things like that, and I would have missed it. Maybe I'll mention that in the room chat.
So we'll start in 2 minutes. Thank you everyone for coming. This will be a really interesting talk. Yeah, I hope everyone is having a really great day so far. How's your Wednesday, middle of the week going, everyone?
Sorry, I was facing that problem where you have to close the file before you can get back to your mute and unmute.
I know. It's so annoying that you have to kind of switch back to unmute yourself. I had that times.
Yeah, I always open it in Chrome so I can just switch back on the phone, back and forth.
I think I'll end up doing that, yeah.
Yeah, it's the same complaint. And usually, if possible, I use a desktop beside me to for the separate screen. For Brett, thanks very much for the providing this link. Very thoughtful and very helpful. Yeah, it's
Sure, yeah.
opens note just very smoothly. Thank you.
It's really cool you found cyanonapthalene in space.
Well,
should
I
say.
think so. I'm glad you think so too.
This is a really interesting paper. I'm actually quite excited to hear this talk, actually.
Awesome.
Have you had a good day so far, Doctor?
Oh yeah, it's been great. I just got back from cheering on my friends at their softball game that was in the middle of the pouring rain. So
Oh no!
nice to
Did
be
they win?
indoors and warm and dry finally. Yeah, we got
Did,
soaked.
did they win at least?
Oh no, absolutely not.
Oh no! So it was just
But
moral support then.
exactly. They had fun though. That's all that matters.
That's what people that don't win always say.
Fair.
No, it's good they had fun though. But now you can enjoy your evening and share some science with us.
Yeah,
Actually,
exactly.
you go from underneath the clouds to above the clouds, aren't you?
Yeah.
Yeah, I think we can slowly start. Yeah, it's already 9:01, I think. So, yeah, welcome everyone to the Science Society. We are very honored to have our guest speaker here today to talk about his really cool space research. And let me give you a little bit of information. Dr. Brett McGuire, he's assistant professor in the Department of Chemistry at the Massachusetts Institute of Technology and adjunct assistant astronomer at the National Radio Astronomy Observatory. He did his PhD in physical chemistry at the California Institute of Technology and his master's in science and physical chemistry at Emory University. And his bachelor in chemistry with the highest distinction at the University of Illinois. Yeah, currently, as I said, he's at the MIT, and yeah, he is received different honors and awards, and he published a lot of different papers, and we are very honored to have you here talking about your latest research, as we can see in the title. And I'll share in the chat also the paper, the actual paper, if people want to go ahead later on or look at it again. I shared it also on Twitter, if you follow us on Twitter. So yeah, Victoria, would you like to ask Brett a few questions before he starts with this presentation? Thank you.
Thank you. I'd be so happy to. And look at that really great smile. That's fantastic. Love the new profile pic, Brett.
Thanks.
This just makes me so happy. Okay, so Science Society welcomes you, and as you heard, we're so super excited that you're here, because who doesn't want to hear about molecules in space and new molecules at that? So my question to you is to help our audience and listeners of the replays to get a little bit of an idea about who you are as a person, in addition to your work. So my question is, when did you first notice that you felt an affinity for science as an interest in your life? And that could be something more recent, or it could be in your childhood, an experience or a person, or anything that sort of tipped you off that you were feeling sciencey?
Sure. Well, so my dad actually is a professor of chemistry at a small little state school in Illinois called Eastern Illinois University. If you're familiar with Tony Romo of the Dallas Cowboys, it's where he played his college football. So there's this really fantastic picture that mom and dad dug up a few years back of dad giving me my first periodic table at an age of, I think, 6 days old. So I've kind of been in the chemistry family for a very long time. So I always enjoyed science and science fiction growing up, but I had a really fantastic chemistry teacher in high school, and then needed to study something when I went to college. So decided to major in chemistry, and it's all kind of been downhill from there. And just have never escaped from the wonderful world of studying molecules.
Wow, I think when you say downhill, you mean more like naturally, like coasting, like it's the momentum is there, not
Sure,
that
yeah,
it's
yeah,
negative.
exactly. Yep.
Okay. Yeah, it's such a great story. I also not at 6 days old, but maybe like 3 months old. I remember giving my firstborn a plastic periodic table
Oh,
because I thought
nice.
that could be really cool to teethe on. What was your favorite element? Do you remember?
Oh, from when I was well, I don't remember what my favorite element was as a kid. I do remember my favorite element in high school, and it was element number 111. And I liked it because it was unium, which was the temporary name that was given to it after it was discovered, but before the International Union of Pure and Applied Chemistry decided what to actually call it. I have absolutely no idea what it's named now. It's named after somebody, but that was always the my favorite in high school, just because it had a funny sounding name.
Oh, that's great. No, I wonder if it's rentunium
Oh, could be. Sure,
element.
yeah.
Yeah, it looks like
111.
yeah. Yeah, so thank you. And can you tell us from that point and somewhere along that downhill path, how you arrived at the work that you're doing today?
Yeah, sure. So, um, I went to U of I and did a year of chemistry there. And then Dad, kind of poked me the summer after my freshman year and said, "Hey, if you actually want to do this and go to grad school, you probably need to do some undergraduate research." So I said, "Fine." I went back to school and started, gradually looking around for something to do. And it just so happened that this young assistant professor was giving a talk one night specifically to try to attract undergraduates to work in his group. And I'm doing a disservice to his research, but he basically got up in front of all of us and said, "Hey, I blow shit up and then hit it with lasers and look for it in space." And that was it. I was hooked. This is awesome. I don't have to mix things in beakers. I get to use lasers. I'm there. So I joined his lab and just started doing chemistry experiments. His group was unique because he had both chemists and astronomers sitting in the same offices. So I was a chemist. I didn't know astronomy, but my desk was right next to an astronomy graduate student. So I sort of picked some stuff up by osmosis, and then gradually over the course of graduate school, about 2.5 or 3 years in, I started doing radio astronomy of my own, looking for the molecules in space that I was studying in the lab. And at this point, I do about 50-50. So about half the time I'm working with observational astronomy data, and half the time well, not me, my students now are in the lab working to measure the spectra and explore those molecules here on Earth. So it's a really great mix, and I'm kind of shocked at the path that brought me here, but I wouldn't ask it for any other way. It's a wonderful field.
And so fortunate that you had that cross-disciplinary opportunity too with the astronomers. And geez, who wouldn't want to blow shit up in space.
Can I just
Exactly.
And look for
can
it. I love
can
that.
I just oh,
And
sorry,
look for it.
can I just say, Doctor, I've heard a lot of talks at the beginning about how someone got to somewhere. This is the first time I want to go, how do I sign up to that? Thank you.
Absolutely.
So that was amazing, as I'm sure you are aware, because you're doing it. So at this point, you're welcome to launch into your discussion of your work. And some guests prefer to give their talk and then have a Q&A following the talk, and some prefer to have the Q&A alongside. So that's entirely up to you, and we will do everything else that is required of, guests and things. But please take the mic and enjoy your time.
All right, thanks. So, as might have mentioned or heard in the lead up here, if you click the link that's pinned at the top of this room, I'm kind of new to the interface here, but I think also might be dropped in the chat there, bit.ly/club22, bam, my initials there. It'll take you to a page that has a script. So in addition to being really excited to be here today and to share with you the work that my colleagues and I are doing, I've tried to prepare here an easier way to follow along. So over the course of the pandemic, I've experimented quite a bit with different ways of effectively presenting online lectures, both in the classroom, and that's the first time I've ever given an audio-only talk, which is exciting. But one of the things I found people most like is when I do this, when I provide a script of what I'm planning to say on each slide. It makes it a little easier to follow along. So if you follow that link, you'll find I've posted one for this talk. There's also a link at the top of the script, which will take you to PDF slides that you can follow along with if you'd like, with some graphics and other things. Now, if you are looking at the script, this last line here for this slide, fair warning, despite quite a bit of practice, I'm still not perfect at following my script, but I will try my best. So if you go ahead and move to the second slide here, I just want to start off with a really big picture view. So the field I'm in is called astrochemistry. I'm an astrochemist, and to me, astrochemistry is the study of molecules in space, where they are, how they got there, and what they're doing. If we move to slide 3 here, we can see that chemistry is occurring at every step along the process of forming stars and planets. We can go all the way back to the Big Bang, where we have the formation of hydrogen and helium and a smattering of heavier elements like lithium. But it really wasn't until the first stars were born, processed those lighter elements into the more complex ones like carbon, oxygen, and nitrogen, and then died, that chemistry as we know it today, real organic carbon-based chemistry, got started. And it's in these stellar nurseries, the cold, dark clouds of gas and dust, where chemical reactions are constantly building up complexity in the molecular inventory, even at 10 Kelvin, as cold as these clouds are, 10 degrees above absolute zero. Now, eventually a star is going to turn on, and that star is going to inject heat and energy into the system, and that's going to drive yet more complex chemical reactions. We also know now that around almost all of these new stars, planets will eventually form, and those planets are going to be constantly bombarded with the chemical remnants of their natal molecular cloud as meteorites and comets crash down upon the surface, delivering the raw organic materials that, on at least one example we know of, leads to the formation of life. And of course, that life and the system will be consumed in one cataclysmic apocalypse or another at some point, and the chemical materials are ejected back into the interstellar medium to start the cycle over again. And the real point here, the point I'm trying to make, is that chemistry is evolving with and shaping every step of this process of forming stars and planets. And what I want to know is how, on a detailed reaction by reaction basis, that chemistry is happening. What molecules are present at what different stages? How are they shaping and being shaped by the physical conditions of the source? And what can they tell us about the different sources we're seeing them in themselves? So if we head to slide number 4 here, a large part of the talk today is about identifying molecules in space. And it turns out we're really good at doing that. As of today, we've detected more than 250 individual unique chemical species outside our solar system. The slide here actually is already out of date, even though it was made last fall. We're really cranking out the new detections of molecules outside our solar system. The last few years have seen detections at nearly once a month, which is just, trust me, completely insane. The number of molecules detected outside our solar system has about doubled since I started undergrad. And I'm old, but I'm not that old. So today, I want to ask a very specific question and talk about a very specific class of molecules, not just molecules in general. And the question I want to ask is on slide number 5 here. And that question is, where are the rings? And by that, I mean, if you look in the chemical abstract services, it's a giant database of all molecules known to or dreamt of by humanity. Something like 80% of them contain a ring of either 5 or 6 atoms bonded together somewhere in their structure. And these aren't crazy, weird, esoteric molecules either. They're things we encounter in our everyday lives. They're found in amino acids, the Lego-like molecular building blocks of our proteins. They're found in our food and our drinks, such as in caffeine. And they're found in our medicines, like ibuprofen. But there's actually something really weird with ringed molecules, and that's on slide number 6 here. And we're going to look at the history of detecting molecules in space. And what this graph here shows is the cumulative number of molecules detected in a given year outside our solar system. We didn't detect a 5 or a 6-membered ring species until 2001. That's a 6-atom molecule called benzene, shown on this slide here. It's 6 carbon atoms bonded into a ring, and each one of those has a hydrogen attached to it. It's very simple. It's just carbon and hydrogen. And we spent 3/4 of a century cataloging molecules in space without ever seeing one of these rings that play such an essential role in chemistry here on Earth. And in fact, after we detected benzene in 2001, it wasn't for almost another 2 decades that we started to detect others. It's only been in the last few years, since 2018, that we've seen a real explosion in our knowledge of cyclic, and now, as we'll talk about later, polycyclic molecules in the ISM. So today I want to talk a bit more about these new discoveries, specifically about why these molecules are important. And they're important both astrophysically and pretty close to home here. And why we're having such a hard time explaining the weird places we're seeing them in and weird quantities we're finding them in. So if we head over to slide 7 here, you'll see that I lied to you just a few minutes ago when I said we hadn't detected 5 and 6-membered rings in space until quite recently. We've actually had pretty strong circumstantial evidence for their existence since the mid-1980s. Actually, the first real paper on this came out just a few months after I was born in 87. Now, depending on who you ask, something like 10 to 25% of all interstellar carbon is in fact locked up, contained in molecules in aromatic rings. They're molecules called polycyclic aromatic hydrocarbons. I have a few examples here on the slide, but just to describe these to you, these are very large molecules where we take anywhere from 2 rings of 5 or 6 atoms to dozens of rings of 5 or 6 atoms, and we fuse them all together to form a single molecule. And we know, or at least we very, very strongly suspect, that these are out there because of the widespread, bright, and distinctive features we see in the infrared in regions of our galaxy that have strong ultraviolet fields, as well as a host of external galaxies. These are emission signals that we observe with infrared telescopes. And I zoom in on this on slide 8 here, talk a little bit more about those signals. See, the problem is that these emission signals that we're seeing with our infrared telescopes, well, they're not labeled with the names of the molecules giving rise to them. Instead, what we're seeing are the characteristic features that we would expect to see from aromatic, so ring-containing molecules in general. These are the patterns of light these molecules give off or absorb as the carbon and hydrogen atoms within them stretch and bend in vibrational motion. Now, That's not to say that the vibrational signatures of different PAHs aren't unique. They are. Actually, they're quite a bit like fingerprints. If you give me a handful of different PAH molecules, polycyclic aromatic hydrocarbons, in the laboratory and give me an appropriately high resolution spectrometer to measure them, I could separate them out because their spectra are unique. They're fingerprints. But in space, we have a bit of a problem. There are just so many different PAHs, and their spectra, their fingerprints, while all unique, are actually quite similar. So the signals all overlap. We can tell they're almost certainly coming from a collection of PAHs. We just can't tell which ones. It's like a giant choir all singing the same song. Any individual's voice is unique, but good luck picking it out from the crowd when they're all singing together. So that's actually a problem for those of us that want to study the chemistry of carbon in space. Since we can't identify any of these molecules individually, we can't piece together how they form and evolve. We don't have any detailed access to as much as a quarter, 25% of all the carbon in space. And as a chemist, that's super embarrassing because here on Earth, we actually understand PAH chemistry relatively well. So we move on to slide 9 here. We see that PAHs are one of the primary byproducts of incomplete fossil fuel combustion. So if your car is not burning cleanly, or if your grill is not burning cleanly, or if any of the dead dinosaurs were burning or not burning cleanly, they're producing PAHs as one of the byproducts. They're also one of the big constituents of the char marks on cooked meats and vegetables. And both of these are actually pretty big problems because PAHs are great nucleation sites for forming pollutant atmospheric aerosols, which go on to make a ton of nasty, environmentally hazardous stuff in our atmosphere. And they're also pretty carcinogenic, so when we're eating them, they're giving us cancer. So on slide 10 here, we can see that, as you might imagine, this has led to a lot of research into how they're formed and how they react here on Earth, so we can understand what's going on with them in our atmosphere and in our foods. Now, there's a number of different chemical pathways, but the pathways all tend to look pretty similar. You start out with a single ring of atoms, say benzene, right? And then you bring in a few more carbon atoms at a time, maybe some hydrogens, and you first add a little side chain and then another, and those side chains gradually wrap around to connect and form a new ring. And you just repeat this process over and over and over to build up these larger PAHs. And it turns out these processes are really efficient in the important environments here on Earth, high temperature environments in flames, when we're burning things, when we're grilling things. But it turns out there's a problem in space. You see, each of these steps, every time we want to add carbons to these rings, it requires energy. Energy that is plentiful in flames. Flames are hot, right? But that energy is nearly entirely absent in almost all interstellar environments. All of these cold, dark molecular clouds that I told you earlier, there's a lot of chemistry happening. Well, there's no energy there to drive these particular reactions that we know form PAHs. So if we move on to slide 11 here, we can see that after a few years of debate, so in the late 80s, we kind of settled on PAHs being products of the few high temperature environments where we might find them in space. And those environments are places like old carbon stars at the end of their lives. These stars literally act like sooting candles. They output tons of carbon black into space, where the very high temperatures in the immediate surroundings of their stellar atmospheres allow PAHs to grow, to undergo these reactions that require energy. And then as they leave the formation region, as they no longer have that energy, they can't be formed anymore, some of them start to get broken back down by the harsh UV radiation fields from the star itself into smaller and smaller sizes, until eventually they leave the star's influence altogether, traverse the ISM over hundreds of thousands or millions of years, and float their way into the other regions where we see them today. And this hypothesis makes sense. We know these reactions work, that they work here on Earth, And these environments, these warm environments, are the places where we actually detect them using our infrared telescopes. But look, there's nothing to say that we can't also build them up in the cold, dark clouds of atoms and molecules where stars will eventually form, but haven't formed yet. The raw building blocks of carbon and hydrogen are there already, the small molecules we need to piece them together. We just need to build the complexity up through chemical reactions, and ones that don't require energy to go. Now, that route, building from the small little pieces, is what's sometimes called the bottom-up route, as opposed to the top-down route that originates in high-temperature environments. The key is that, well, we don't know what reactions could actually lead to the formation of molecules from the bottom-up route. The building blocks are there. There should be something that makes them go, in theory. We just don't know what those reactions are because we haven't studied them here on Earth. And actually, to add to that problem, we've never actually, until very recently, as I'll talk about, detected PAHs in these cold pre-stellar cores where stars haven't started forming. So if we did want to investigate these two different regimes observationally, and maybe perhaps dig back into the question of whether bottom-up routes were viable at all, then we'd probably want to start with the smallest aromatic molecule, the smallest ring. Sorry, my AirPods here seem to have jumped to being connected to another device. All right, can you still hear me?
Yes, we hear you really well.
Perfect, awesome. All right, so the molecule that we want to look for, right, is that simplest ringed aromatic molecule, benzene, right? That six-membered ring that's just carbon and hydrogen. That'd be a great place to start. But there's a problem. It's really, really hard to search for benzene in space, as it turns out. There's a couple different spectroscopic signatures we typically look for to identify molecules in space. And one of them we've already talked about, the vibrational fingerprint of molecules. Unfortunately for us, benzene's vibrational spectra, its fingerprint, are entirely blocked by Earth's atmosphere. The gases in Earth's atmosphere just absorb all of the light at the wavelengths, the colors of benzene's vibrational spectra. So we can't observe benzene from the ground. We need a space-based telescope, of which very few have ever operated at the right wavelengths. So we've actually only detected benzene in a couple of places in space. Kind of hopeful that the JWST, which launched earlier this year and is just about ready to start taking data, might give us some new insights. But even more commonly than that, something like 90% of the molecules we detect in space are seen not through their vibrational spectra, but through their rotational spectra. Right? These rotational spectra are the characteristic patterns of light that the molecules give off, not as they vibrate, but as they tumble freely end over end in space. And each pattern, each rotational spectra, is unique to that molecule. So no two different molecules can have the same frequencies of light in the radio wavelengths that they give off while they rotate end over end in space. So on slide 12, I actually show you exactly how it works to detect a new molecule in space. What we do is we measure the rotational spectrum of a molecule of interest here on Earth in the laboratory. And then we match it to that same pattern observed with radio telescopes in space. Now this slide here shows an example radio spectrum of a source called TMC1, that I'll get back to in a second, up in top in black, taken by me with the Green Bank telescope, which I'll again get back to in just a second. And if I overlay the spectrum of a molecule measured in the laboratory, in this case CH2CN, that's down below in red. You'll see it's an exact match for the observations, right? The exact same spikes, the exact same pattern of light shows up in the laboratory as it does in our observational spectra. There is no other molecule in the universe that could have this exact set of frequencies because they arise this way due to the arrangement of the atoms within this molecule. And it really is that simple. Now, sometimes we have to work really hard to see these signals. Sometimes they're really weak. Sometimes they're confused with other signals. So it can get a little trickier, but this is actually the process of detecting a molecule in space. Now, unfortunately for us, benzene doesn't have a rotational spectrum. One thing I forgot to tell you about these spectra, these fingerprints, is that the molecule must be asymmetric. Benzene is just too perfect. The ring is the same no matter how you look at it. So as far as light is concerned, it's not possible to see it rotating, because as it spins end over end, it looks the same from any angle. On slide 13, though, I'll tell you how we're going to get around this, because I'm a chemist. And if there's benzene in any place in space and any amount of the cyanide radical, so a carbon bonded to a nitrogen, and there's a ton of cyanide radical in space, we should be able to detect a very closely related molecule to benzene. It's called benzonitrile. We just remove one of the hydrogen atoms that decorate the outer edge of benzene and add the CN group instead. And this makes the molecule asymmetric, so it has a nice rotational spectrum for us to search for. That just leaves us asking the question of which dark cloud to search in. Now, if you're looking for molecules in a dark cloud, there is no better place historically than TMC1. This is at one end of the Taurus Molecular Cloud, so TMC, in the constellation of Taurus itself. There's only one other place in the galaxy, Sagittarius B2, that's actually a star-forming region very close to Sag A star, the supermassive black hole at the center of our galaxy that the Event Horizon Telescope showed us a very nice image of its blurry donut last week. Only that one place, Sagittarius B2, has boasted more new molecule detections than TMC1. And finally, if you're looking to do centimeter wavelength observations, there is no better telescope than the Green Bank telescope. This radio telescope is 100 meters across. That's an entire football field for us Americans. You even have enough room for grandstand seating on the edges and that tiny little room where Tom Brady deflates his footballs. It's the most massive, fully steerable object on land, and really the only way to beat it is to go out to the ocean and be an aircraft carrier. And as an added bonus, it's located in the National Radio Quiet Zone in Green Bank, West Virginia, meaning there's very little interference from pesky things like cell phone towers or Wi-Fi or microwaves. All of our microwaves are in Faraday cages. So slide 14, very briefly here, shows you that this is exactly what we did a few years back. We found signal from benzonitrile's rotational spectra exactly where we measured it in the laboratory by using the GBT to look at TMC1. Now on slide 15, you'll see that this got us all excited. And I set up a large collaboration to study TMC1 and see whether there really was a hidden treasure trove of new carbon chemistry to be found there. Now, if you've ever encountered a professional astronomy project before, you'll know that we are required by astronomer law to have an acronym. So we are GBT observations of TMC1, hunting aromatic molecules, which spells out Gotham. So the slide here has our legally dissimilar logo that we're quite proud of, made of actual benzonitrile spectra measured from space. So slide 16 tells you what Gotham actually is. I think it's important to highlight all of our fantastic team members here. We're a pretty ragtag team of students, postdocs, junior faculty, and some established researchers from a very wide range of universities and continents, all dedicated to studying carbon chemistry, aromatic chemistry, at the earliest stages of star formation. We're largely divided into 3 subgroups that focus on observations, laboratory work, and astrochemical modeling. But of course, almost everybody lives in multiple groups simultaneously. So slide 17 shows you the primary product of our observational portion of our collaboration. It's a high resolution, high sensitivity spectral line survey of the source. So what does that mean? Well, it means that rather than looking for the rotational spectral patterns of one molecule at a time, like we did for benzonitrile, we just say, screw it. We're going to look at everything in the source simultaneously. We're going to collect the rotational spectrum of all molecules present and just see what's there. Once the survey has finished, we're releasing it publicly in fully reduced form alongside each of the papers that describes the work. So You can already get some of our data if you actually want to go play with it, and more will be done soon. The last of our observations will conclude in August of this year. So slide 18 shows you what we've seen with Gotham so far. We've seen an incredible array of new molecules, 14 of them to be precise. I've thrown them all up on the slide here. Each of these molecules was detected in space for the very first time known to humanity by our Gotham collaboration. And we're really proud of this little rogues gallery of new chemistry, especially of the new ringed species we've been finding. Now, combined with benzene and some additional discoveries by another team who's started to look at the source following our own discovery of benzonitrile, we actually now have quite the picture of 5- and 6-ringed species in space. In fact, we've now detected 9 total 5- and 6-ringed species, including 3 PAH molecules, each made of 2 fused rings. So that's the 1 and 2 cyanonapthalene that we highlight in the paper that was linked for the talk, as well as a molecule called indene, which is a 6-membered ring and a 5-membered ring bonded together. And remember, until 2018, benzene was the only one known out of those 9. So that leaves us asking a couple more questions, and I'll try to answer those in the last few minutes here. The first question is this chemistry widespread? If it's just something that's unique to TMC1, if TMC1 is some sort of unicorn in the sky, well, that's interesting, certainly interesting to me, but it's not generally applicable. Maybe it doesn't affect our overall view of carbon chemistry, of aromatic chemistry during the star and planet forming cycle. So we want to ask, how common is this potential bottom-up chemistry at forming rings and PAHs in dark clouds at the early stages of star formation? And the second question that we want to ask is, can we explain why we're seeing it here? Can we actually answer how does it proceed in these low temperature environments? So slide 19 answers that first question. We set up a sub-project within Gotham, appropriately acronymed ARCM. This is a rigorous K-band hunt for aromatic molecules, K-band meaning somewhere between 15 and 27 or 35 gigahertz, depending on who you ask. We named the different frequency ranges that radio telescopes and radio receivers operate in a very dumb manner during the Second World War to try to disguise the different frequencies that the radios were operating in. I think it's very confusing. So anyways, ARCM, what did we do? We targeted a number of other dark clouds, so things not TMC1, within a different region. So in this time, it was in the Serpens Molecular Cloud, which is, you guessed it, in the Serpens constellation, to search for benzonitrile again as a proxy for this new chemistry of rings that we're seeing. And we were actually pretty shocked by the results. We ended up getting detections, and strong detections, in many of the different cores that we targeted. So this leads us to believe that the chemistry is not actually isolated to TMC1 and is indeed a general phenomenon that's influencing chemistry at the earliest stages of star formation. So ARCM is now expanding out to other sources to try to get a larger sample size and to look at places maybe a scotch further in evolution from dark clouds. Maybe a star is thinking hard about turning on, and what's going to happen to the chemistry there. Slide 20, though, addresses the second question, which is much harder. Can we explain what we're seeing? Well, for that, we have a crack team of astrochemical modelers hard at work. Now, astrochemical modeling, in broad strokes, works in 2 parts. The first thing that we do is we build a massive network of molecules of interest and all of the reactions between them. These include things like the rates of reactions, relative importance of the pathways, grain surface and gas phase routes, the influence of ultraviolet radiation, energetics, and more. And these networks describe how our molecules react and evolve, and how physical conditions like temperature and density alter how these reactions occur. It's a grand web tapestry of chemical reactions. And then second, we have the model itself, the model of the source that we're studying. These models impose the physical conditions, sometimes time variable to simulate maybe the turning on and warming up of a star. Right? And then we solve this huge matrix of coupled differential equations that describe how molecules will react under those conditions with time. And what you get out is a series of time steps and the abundances of molecules that our model predicts, based on our understanding of the chemistry, will happen at each of these different times. And ideally, you'd like your model to reproduce the abundance that you see with your observations. And on slide 21, you can see sometimes the model actually does really well. So for relatively simple, non-cyclic species, our model does a pretty darn good job of reproducing the abundances that we see in TMC1. And by pretty good job, I mean within a factor of 2 or 3. Astronomically speaking, that's perfect agreement. Actually, anything within a factor of 10 is pretty good, and really, we get within a factor of 10 for basically all of the simple species that we're seeing in TMC1. Now, I mean, we're good, but this really isn't all that surprising. These molecules are well known and have long been studied, not just with models, but also observationally and in the laboratories. We have decades of experience to build upon in studying this chemistry. On slide 22, though, you can see how we do for explaining our PAHs, like 1 and 2 cyanonapthalene, those 2-ringed species we've discovered. The outlook isn't nearly as good. Our models underpredict the abundance of PAHs by 6 orders of magnitude. That's a factor of 1,000,000. Now, that's for a preliminary guess at some of the bottom-up reactions that could be occurring. Remember, we're kind of making this up as we go along. These low-temperature pathways aren't really studied since they're not important here on Earth. We don't have 3, 4, 5 decades of prior work to build on like we did for those simpler molecules. Slide 23, though, is showing you that as time goes on, we are continuing to add new reactions to our network, including not just ones that we've dreamt up, but reactions actually measured in the laboratory, like done by a guy by the name of Ralph Kaiser at Hawaii, who has one of the very few instruments in the world capable of measuring and probing the dynamics of these reactions under astrophysically relevant conditions. And as we add this new information to our model, we're improving. Our latest models are only off by 4 orders of magnitude, which is a lot, but that's a factor of 100 improvement, and we did that over the course of maybe 6 months. So we're still a ways off, but we're making steady progress here on bringing the models, our understanding of the chemistry, into alignment with reality. So what are we going to do to try to continue to improve? Well, on the one hand, we're just going to have to wait for folks like Ralph to measure new and exciting potential reactions in the laboratory, and that takes a lot of time. They're really hard experiments. But while we wait, we're doing our best using computational methods to approximate the reaction conditions and expand our networks that way. And we're also hard at work trying to detect new molecules that might be influencing the chemistry, and thus might be important for completing our models, but that we haven't yet seen in space at all. And sometimes molecules we haven't even seen on Earth yet. So this includes a laboratory team that's busy measuring the spectra of new and exciting molecules here on Earth, and our observational team looking for those molecules constantly as our data continues to pour in on TMC1 from the Green Bank telescope. It's going to be a really long process. It will be years, if not decades yet, before the potential of TMC1 is really fulfilled at unveiling the carbon chemistry that's occurring in space here. We're really just at the tip of this exciting iceberg, and I really can't wait to see where we go next from here. So the last slide is just an acknowledgement slide here, acknowledging my new group at MIT, 3 fantastic first-year graduate students and a wonderful, wonderful postdoc, various affiliations and funding sources for my work, a huge array of collaborators in this word cloud, and all of the different ways in touch with me online. And I'm more than happy to take any questions that you might have at this point. So thanks for showing up and listening in.
Thank you so much for this amazing talk. That was really wonderful. Yeah, it was quite delightful. And I think you pulled us all into that we regret now that we didn't go the same career path.
Wow. Wow. Just wow. Wow.
So please flash your mics if you have questions. Serena, go ahead.
Really fascinating talk. So, first, the loaded question. I didn't see purines or pyrimidines on the list. Are we looking for those, or they're just hard to find, or have we just not found them yet?
Boy, that's a fantastic question. Purines, pyrimidines, pyridines, perols, for folks in the audience, a lot of these are molecules that have, we call them heterocycles. So they have nitrogens or other molecules that aren't carbon as part of that cyclic ring. Or maybe they're decorated with amine groups, so NH2, or ammonia groups, NH3, on the outside of the ring. We are looking for these. We have the spectra of many of the very simple ones that might be most likely to be found measured in the laboratory. They're not present in the source. They don't show up in our spectra at very high confidence. And that's really weird. We actually see these molecules in comets and meteorites, so we know they're made at some point, but they don't seem to be present here in any large abundance. We suspect this probably has something to do with amine, so NH2 and NH3 chemistry, not actually being very efficient at these temperatures. So something about those reactions is preventing the formation of these molecules in the source, we think. That is not going to stop us from continually looking for these molecules as well.
Really cool. On the modeling, I imagine, I'm trying to sort of think through the reaction mechanisms. Does your model, would you say it's reasonable to assume that there's a fair amount of the populations of these things that are in excited states? And does your model incorporate that in its reaction kinetics?
That's a great question. So the answer is that at any given time, the steady state abundance of molecules in an excited state is going to be very low. And that's because as soon as things get excited in space, probably one of two things is going to happen. Either they're going to de-excite themselves by emitting a photon and just relaxing, if they're in the gas phase, or they're going to be very uncomfortable and either give away that energy by dispersing it onto the surface of an interstellar dust grain that they might be stuck on, or just blowing apart. There are a few exceptions to that, and our model does take into account some very key pathways where molecules can become excited by, say, a cosmic ray or a UV photon or a secondary electron from some sort of energetic process. And certain molecules can live long enough to then overcome reaction barriers and go on to react with other things. The incorporation of this into astrochemical models is brand new. The person sort of leading the charge is a young assistant professor by the name of Chris Shingeldecker, who sort of spearheaded all of this about 3 years ago while he was still a graduate student. And fortunately for us, he's on our team. So he is incorporating this into the models, and hopefully that might help to explain some of our deficiencies. But it's a very rare occurrence, we think, in space, but maybe an important one in the times it does happen.
So that's interesting. So the dominant mechanism then is just direct addition through collisions, in essence, a kinetic?
It is. So in the gas phase, the dominant reaction pathway is an ion molecule one. So the average time between collision for two neutral species can be quite long. It can be something like days to months. But if one of the molecules is an ion, then the positive or negative charge on the ion affects the electrons on a neutral molecule and will pull it in like a magnet and cause that collision to happen faster. And those collisions between ions and neutrals are usually barrierless. They don't require energy to go. So that works in the gas phase. And then for molecules that are frozen out on the surface of interstellar dust, sort of the primary way that reactions are driven are by being bombarded by hydrogen from the molecular cloud.
Let's see. Okay. Well, thank you.
Sure.
Hey, I can't. I jumped on stage to ask one question.
Sure.
Now we know I love these subjects. I'm like scientific minded. I was going to be a scientist astronaut, but until I fucked up. But anyway, we know a lot of the great scientists have done it, and we know a lot of stupid people have done it. And people, we're not going to mix spirituality and science, right? And maybe they're not even separated, right? But a lot of fools do it, and they project into these projections and stuff. But as highly intelligent people, which a lot of the scientists, great scientists have done it. Have you not in the woods in the jungle trying to get awakened, but have you just done psychedelics and only grounded yourself in these scientific ideas and like open up the vision and see the molecules and like go straight scientific psychedelic experience and see if you could see how the stuff is created?
Sure, sure. I haven't personally, although I do have several friends and colleagues who have had good experiences on psychedelics, and it works for them, and that's fantastic. But no, not me personally. Sorry.
Thank you. Let's have people show a flash of mics, and then we can see who is going to go next with their question. And I squeezed in here because I just want to say thank you so much, Brett. I love how on your slides you have words like, please use our data and publicly available. I wish more people would do that because, we got to
Me,
work as a collective.
me too. I wish other people would give me their data as well. That, I figure if we put ours out there, maybe they'll give us theirs in return.
Fantastic example. Okay, friends, flash some mics, please. And let's see who's going next. All right. Katarina, did I see you flash your mic?
No, I think Ankit, he flashed his mic. Hi, Ankit. How are you?
Hi, Ankit.
Hello.
Thank you.
Yeah, hi. Fantastic talk. I was just wondering, uh, I have a few questions. So one of the questions is that uh, a, a follow up from Serena's question that are other exotic reactions possible? Specifically, this question is directed to the cyclopentadiene sort of molecules that you discovered in space. So are Diels order possible in these conditions?
Maybe not at 10 Kelvin in this source, but on the surfaces of dust grains, once a star has turned on and heated up the gas to something like 2 or 300 Kelvin, at that point you can, as long as it's a two molecule process for the most part, you can drive basically any uncatalyzed organic synthesis reaction that you want. The efficiency of that, I'm not sure, but yeah, more or less any chemical process that would work in a beaker here on Earth, between just two molecules, getting any three molecules together is a hard trick given the density. But just two molecules in most cases would work in those regions. But I think once a star really has to be around to drive some energy into the system for that for a lot of these to become unlocked.
Hmm. That's interesting. Yeah. My next question is actually perhaps much more naive. From the rotation, you mentioned that you look at rotational spectra of molecules for
Mm-hmm.
signature. And then you compare it with synthetic molecules that you make and look at their signatures. Uh,
Mm-hmm.
is the rotational spectra coming from space affected by Doppler effect as well? And is that something you look into?
Great question. It absolutely is. So all of the places that we're looking at are moving toward or away from us, and the molecules are moving toward or away from us as well. In TMC1, in particular, the cloud itself is moving at a velocity of 5.8 kilometers per second. And so all of the frequencies that we see are shifted by that amount. But the entire rotational spectrum, all of the lines are equally shifted. They apply
Uh,
the same Doppler shift to it. And the way that we typically figure out what that shift is that we look for the characteristic line of carbon monoxide, so CO, which the rotational spectrum arises at 115.3 gigahertz, and it will be the brightest line that you see. So carbon monoxide is the most abundant molecule in space other than molecular hydrogen. So it's a whoppingly bright line that you cannot screw up. You can't mistake it for anything else. So you look for that line and you say, how far is it shifted from where it's supposed to be? And that tells you the Doppler velocity of your source and all of the other molecules in it.
Oh, fair. That's good. And
I do.
I have a last question, and this is perhaps also naive, but I understand that your area of field is polyaromatic hydrocarbons. But in the earlier parts of your slides, you actually showed the list of molecules that are present in interstellar space, and I
Mm-hmm.
was just curious. Uh, there were a lot of magnesium atoms in that list. I'm just curious why.
Yeah, I'm curious too. So magnesium is these molecules are primarily found in two places, and they're both old dying stars. So one of them is actually IRC plus 10216. It's I actually showed a picture of it in slide 11 on the left, that little sphere that the PAHs are coming from, an old carbon star. And the other place that we typically see these is a hypergiant star, a red hypergiant called VY Canis Majoris. So it seems to be that the conditions necessary to make magnesium molecules to be detected in the gas phase, like we do with our rotational spectra, are very high temperature environments. And my guess is that's what's happening is that these high temperature environments are and violent environments are causing interstellar dust grains that are made of magnesium containing minerals to be ground up against one another, releasing the magnesium into the gas phase where it can briefly react, do chemistry, make some simple molecules, let us detect it, and then they'll eventually just freeze back out and form new dust grains. So a lot of the aluminum molecules and silicon molecules that you see on this list as well are also formed in similar fashion.
Thank you, Dr. McGuire. This is fascinating work. Thank you.
Sure, you're quite welcome.
Okay, who's next? Dr. Shaw, would you like to take the mic?
I just want to say thank you so much. That was amazing. But I'm outside. I cannot concentrate on my question. I might ask my question later. I'm in contact with you later. Thank you.
Sure, sounds great.
Dr. Shaw, have you taken up Formula One driving? It sounds.
I mean, I don't know. I mean, I think that apparently each, room that we have, they are related to each other. I don't know. Somehow we can have a journey.
All right. Thank you for being here. Okay, Frank, I see a mic flash. Take it away.
Oh, hi. Thanks. Thank you very much for this excellent talk. I mean, very exciting research, of course. So these slides are, very helpful. And I had a similar, tagging along, pegging along the previous researcher's question. Looking at the same slides, I think that it's number 4. These many molecules already been found. I noticed at the right bottom corner that you have a C60 fullerene listed. So isn't that also a highly symmetrical molecule? And is it let's say same situation with benzene, and you need to find some sort of asymmetrized composite to do it, or has it a different story or not?
Yeah, that's a fantastic question. So in the bottom right of those slides, we have C60. So that's Buckminster fullerene. For those that don't know, it literally looks like a soccer ball with the same pattern of 5 and 6 membered rings. So hexagons and pentagons that you see on a soccer ball. C60 plus, which is the same thing but with a positive charge, and then C70, which I believe is called rugby balline because it looks like a rugby ball. So these are fullerene molecules. They're incredibly highly symmetric. They contain only carbon. And indeed, they have no rotational spectrum to speak of for C60 here. These are all seen through their vibrational or electronic transitions. So actually moving electrons around within the molecule. So C60 and C70 have been detected in a few different sources using both, I believe, ground and space-based observatories, because we are fortunate that I don't think that their strongest transitions are blocked by our atmosphere, like benzenes are. C60 plus is particularly interesting because it is one of the recently identified carriers of what are called the diffuse interstellar bands. Just a really fun short story. Back in 19 teens, an astronomer by the name of Mary Lee Hager was cataloging the absorption lines observed toward a huge number of different stars. So she's observing the light from other stars and looking at the spectrum of light that comes in the visible and the near infrared, and seeing that there's these absorption features that she can't explain, and they're very deep, and they're very sharp, and they're unique, and there's hundreds of them. And it turns out that over the course of maybe 20 or 30 years, folks cataloged something like 800 of these diffuse interstellar bands. And until 2014, humanity had identified exactly 0 molecules that were causing these diffuse interstellar bands. It was deemed the longest standing spectroscopic mystery in the history of mankind, because it was just such an incredible puzzle. Hundreds of different features. Nobody could figure out what was causing them. Going all the way back to Mary Lee Hager's first observations in the early 19 teens, which she does not get credit for, by the way. It, of course, went to some old white dude, but we're trying to correct that. And C60 plus was just in the last, I want to say 6 years ago or so, definitively identified as the carrier of, I believe, 4 of these diffuse interstellar band features. So that was really exciting for those of us in the field. Chemically speaking, these fullerenes are a bit of an enigma. We have a hard time figuring out how they're made exactly, even here on Earth. And so we've kind of just thrown our hands up about how they're synthesized in space. Not entirely certain whether they're connected to the PAHs that we're seeing or not, chemically speaking. But they're super interesting, and they tend to show up after supernova have gone off, which I just think is really cool, because supernova are cool. That was more of an answer than you were probably looking for.
I really appreciate it. And so just quick, if I may quickly, because you mentioned I actually did a Google while you were giving the info on the background. I noticed that it's actually observed by Hubble telescope. So you mentioned the JW Webb, the new great achievement by the great NASA team. By the way, Jim Green, the chief scientist from NASA, is grades the Clubhouse. Run many great rooms on Clubhouse.
Oh, nice.
So yeah, so I'm curious that what if you said you are also give them consultations. What if, given that great potential and capability, what would you be your interest? I would assume it's towards the bullet points that you listed in your slides.
Yeah, absolutely. So I actually, I'm not the lead investigator on any JWST observations by choice, because they're really hard, and I don't have time for that. But I am on a number of different teams, and we have observations specifically targeting 2 different avenues. So 2 different things that JWST is going to give us. One is access to much higher resolutions, higher fidelity spectra of PAHs in the infrared. So what we're really hoping to do is to see whether or not we can get more detailed information on the types of PAHs, maybe the relative size distributions, whether they're charged, ionized or not, in the regions of the galaxy where we've only previously seen them using these sort of lower resolution observations like I showed you on some of the earlier slides. My main interest in that is to see if we can connect the chemistry of the small PAHs that we're seeing in the dark clouds to the chemistry of the much larger collection of PAHs that JWST, the Just Wonderful Space Telescope, will provide and show to us. Sort of tangentially related to that, as far as that team is concerned, but my interest, it'd be great to be able to get more measurements of benzene in space, just in general. We only have about 2.5 detections of this molecule that's so fundamental to chemistry of these rings. So it'd be great to get more measurements of that. And sort of the third way that we're going to use JWST, at least as far as I'm concerned, as I'm on a team that is using it to look at the composition of molecules frozen out on the surfaces of interstellar dust, so as ices. This dust is one of the primary places where chemistry happens, not just in the gas phase where we can see the rotational spectra, but frozen out on these surfaces. And JWST will give us a fantastic high resolution, very high sensitivity, groundbreaking look at the composition of these interstellar ices, unlike anything that we've seen before. So that'll be really exciting. And maybe, who knows, we'll see that PAHs are also formed on the surfaces of these ices in ways that we hadn't expected. So I think our team is scheduled to get the first data in July or August of this summer. So, stand by in the fall for early press releases from our team looking at those topics.
Amazing, thank you. Sorry, Serena, I think I cut you off.
Oh, I thought I was just going to say, I thought Dennis unmiked. You can go to Dennis.
Thank you, Serena. Yeah, that's very exciting. Definitely looking forward to that, Dr. McGuire. Number one, that was a great crash course in astronomy and astrochemistry. If I may suggest maybe chemstronomer, just for fun.
Ooh, nice. Sure.
Really great visual presentation in the slide deck. It makes it very accessible for the visual learners. I was curious about AI modeling in your projections, given that you've been able to get the error rates down and increase the amount of species that we're able to observe. And what are you most excited with regarding James West in terms of your future work? And it's also very exciting that this is an intergenerational endeavor in terms of science.
Yeah, great questions. So I think the most interesting place that we're taking machine learning and artificial intelligence is in our exploration of chemical inventories in space. So what we've done, and we're the first team to do this. This was done by a really fantastic postdoc of mine who was so good he got headhunted away by Intel, and has left science to make way more money than I'll ever make. Is that he used machine learning to feed in the abundances and compositions of all of the molecules that we saw in TMC1. And the way that he did this was ingenious. There's a formalism available called SMILES, SMILES strings, that use ASCII text characters to encode the chemical formula and structure of molecules in a unique way that allows you to assign what is essentially a word to every molecule that includes the structural information. And what he did then is he used a package called mol2vec, which is built on another machine learning package called word2vec. These are natural language processing utilities. They're very similar to, or literally sometimes the same code that is used by things like Siri to interpret what you're saying, right? To learn the words. And so what he did is he used these SMILE strings and these interpreters to teach a machine learning model the language of the molecules that we study in TMC1. And he fed the the model, the abundances, and said, look, here's all of the molecules that we see here. Examine them along hundreds of different dimensions of similarity, right? So do they share the same functional group? Is there a nitrogen atom that is 2 atoms away from a carbon, or 3 atoms away from a carbon? Is there an oxygen in here? And all sorts of other dimensional axes that we can't even picture in our heads as humans. It said, see how they're all related, and then predict for me the abundances of other molecules in the source. And it turns out his machine learning model does an astonishingly good job of reproducing the abundances of molecules we see in TMC1, way better than our astrochemical models do. And in fact, he then went on and said, all right, give me predictions of molecules that probably are present in the source, but that we haven't detected yet. And we published the paper in June of last year, and within a month, 2 of the molecules that he predicted should be present were detected in the source, which is just mind-blowing, at least to
How
me.
exciting.
It's really cool. Now, the downside here is this is just giving us molecules and their abundances. It knows nothing about the reactions, knows nothing about the chemistry. So we're exploring ways to try to incorporate that, but for now, that was the biggest leap forward, and we're trying now to explore that and generalize it to other places in the galaxy, star forming regions and other dark clouds, and see what legs the model has. As far as JWST goes, really for me, it's the high resolution observations of PAHs in other regions, trying to really see whether or not we can correlate the PAHs that we see by their infrared emission to the PAHs that we're seeing with their rotational spectra. Are they related? Are they not related? What can we learn? How can one data set inform the other? That's I'm really looking forward to that personally.
Amazing. When you were mentioning the way that we understand chemistry on Earth and in cosmic chemistry, it sort of reminds me of oceanic vents and how initially folks thought, nothing happens down there, but given the infrared and X-ray and other energetic sources in the universe, it seems like there's some very exciting things in the future in this field.
Oh, I'm biased, but I certainly agree. And by the way, those oceanic black smoke events, I love those too, because I'm big on astrobiology, the origins of life, and that's a good place to generate some chemistry on early Earth.
Stellar nursery is one of my favorite words. Is very very happy to hear you say that several times. Thank you so much for your time and talk.
Sure.
Yeah. So, by the way, nice touch on the credit assignment for the fullerenes. I'm curious though. For some of the molecules that you show, I'm looking at that polyacetylene, and it just strikes me as a curious molecule to be found in space. Certainly to be built up by the kinetic mechanisms. I mean, could that have been a fragmentation product from, or ring opening and dehydrogenation? I mean, it's like, what is that doing? It wouldn't be stable in high heat sources, would it? I'm
Sure.
just curious.
Yeah, great question. So you touched on 2 different topics there, which are great. So one of the ways that we think we actually might be able to make some of our smaller PAHs, and in fact some of the smaller molecules in TMC1 in these cold clouds, is by breaking apart the larger PAHs that were previously made in the top-down route in the carbon stars. So they traverse the ISM and show up in our cloud, and then we bust them apart using cosmic rays or background UV radiation or just chemical reactions opening those rings, as you say. That certainly is going to play a role. We haven't figured out yet what the balance is between breaking those down and building them up from the bottom. It's not one or the other. It will be both. But to your second point, we do know that a lot of these long chain carbons, hydrocarbons and cyanoacetylene, so things all the way up to HC11N, right? They actually are made piece by piece by the addition of little acetylenic units, C2H. usually through some sort of ion molecule reaction. And it's really neat that we can trace this up. We use this, we do that by studying the carbon-13 substitution at different places in the chain, which is mind-blowing, but we actually can detect the rotational spectrum of the different carbon-13s are unique. So we can see that and study how they're made from different pieces. You're right that they're highly reactive, but one of the beautiful things about space is that there's a lot of time between collisions, even for ion molecule collisions. And so a huge number of these molecules would be transient. In fact, when we measure them here on Earth, they live for microseconds. But in space, there's an awful lot of chemistry occurring. So there's a huge number of molecules to start with. And the time between collisions is small enough that a lot of these transient species are long enough lived for us to detect them and to study their influence on the reactive chemistry.
Really cool. So I want to ask you, we've been going for an hour and 15. How much of your time do we still have?
I can probably stretch this for another 15 minutes, and then it's going to be hitting my bedtime, unfortunately.
Okay. Jake, I saw you on mic. Did you have a question?
Yeah, just sort of a clarification. I think I misunderstood at first when you were talking about lasers that it sounded like you were firing lasers into space and then analyzing, what you were seeing. But I think I understand now that you're shooting molecules with lasers here on Earth, and then from the result of that, you're getting a profile of the molecules that you're going to look for in space. Is that right?
Yeah, that's exactly correct. So we use, in the case of lasers, in my undergraduate, we were looking at the infrared, the vibrational spectra of molecules. I've moved a little bit away from lasers now in my own work. So my graduate work, I use lasers to build a brand new spectrometer to study astrophysical ices. And if anybody has worked in the audience has worked with lasers, they are persnickety little bastards. And I got really tired of dealing with their personality issues and crankiness on a day-to-day basis. So it turns out microwave spectra, radio waves, that's where the rotational spectra of molecules arise from. They're much better behaved. I just type a number into my instrument, and synthesizers produce the exact frequency that I want. All I have to do is just plug it into the wall. No waiting for the laser to warm up, no tweaking of mirrors, no realizing that it's humid or the laser just isn't feeling like, showing up to work that day. So it's been a while since I worked with lasers, but that is, you got the gist of it absolutely correct. We use them to study the interaction of light with the molecules here on Earth, and then look for those same interaction signals coming down from space using our telescopes.
Very cool. Thanks.
So do you know when you can expect this new data from James Webb Space Telescope?
Yeah, so the data, I believe that the observations are actually scheduled to start in June in general, and I believe, and again, I could be wrong here, but I believe that at least some of the observations for the teams that I'm on are being taken in June and August, because one of these is what we call early release science. So our team has agreed, in exchange for getting the data taken first, to be the guinea pigs, to learn how to process the data, how to deal with its quirks and idiosyncrasies, how to work out all the bugs in the software from NASA, and to publicly release the data, again, for free for everybody to use, fully reduced, alongside our experiences, to teaching other people what has gone wrong in the data reduction process, what the pitfalls and traps are, and how to prevent that going forward. A couple of the other projects that I'm on are from what are called Cycle 1. So those are taken after the early release science. So those would be taken over the course of fall and winter. But I expect that we'll start seeing data from our teams trickle in August or September, and then have a steady stream for the next year or two as the observations are completed.
Oh, go ahead, Jamie, if you had a question.
Thank you. Amazing, amazing talk, Doctor. My question's actually less specialized because I'm finding it like this stuff is a bit above my head. But one of the things you mentioned about, I was really curious, as you mentioned you found molecules that didn't exist on Earth already.
Yeah, so molecules that we hadn't thought of looking for here on Earth. So this sort of steps back to that idea of really reactive molecules, things that are so reactive or so energetic that here on Earth, if you made them and released them to fly in the room with you right now, they'd immediately bump into oxygen or water or hydrogen or nitrogen, whatever else is floating around in our atmosphere, within fractions of a fraction of a fraction of a second, and immediately react and be destroyed. And that means that a lot of these species here on Earth, there's just never an abundance of them. You can't put them in a bottle, right? And if you look for them in our atmosphere, well, they might be made by some random reaction or process, but they're immediately destroyed again. And then in space, on the other hand, these molecules that are made, well, maybe it's several seconds or minutes or hours before they bump into something and are destroyed. And when you're talking about chemistry happening on the scale of light years, right? Huge, huge, huge scales, massive number of molecules. Well, that actually gives you time to build up enough of these molecules existing at any one given moment for us to study them. So there are methods for us to make them here on Earth. And generally how that we do that is that we take some precursor molecules, so say take benzene and just nitrogen gas, pure on their own, and then we mix them together and literally hit them with a bolt of lightning. So we hit them with a few kilovolts of electricity and break them apart into a bunch of little pieces that have a bunch of energy. And all of those reactions then happen, probably making, in fact, we know making some of these really highly reactive transient species, these really short-lived species that are important in space, but we don't make them here on Earth normally. And then what we do is before they can be destroyed, before they can react away, we shoot them into a vacuum chamber and freeze them out. We cool everything off down to 2 or 5 degrees above absolute zero. We lower the density dramatically so they don't bump into anything else, at least not right away. And they live for a few microseconds, which is long enough for us to probe them using light to measure their rotational spectra so we can get their unique signature and then go look for them in space. Some of the most abundant molecules in space, some of the molecules with some of the brightest signals, are almost impossibly hard to produce and study here on Earth just because they're so highly reactive. It makes them hard to make them in any appreciable quantities here.
That is amazing. It must be pretty exciting to look at molecules that can't exist here, right? And to see like what part is this jigsaw piece play in the grand scale of things, yeah?
Yeah, absolutely. And it's really fun when the discoveries come completely by accident. So two of our 5-membered ring species, those somebody mentioned them earlier, they're called cyanocyclopentadiene. We didn't even think to look for them. We just blew up some molecules and saw a rotational spectrum, a pattern of light that we thought, well, this is weird. We should figure out what molecule this is coming from. And it turned out, using a bunch of tests and assays and experiments I don't have time to get into, we were able to assign those spectra to be from these 2 5-membered ring species. We didn't try to make them. We just made them by accident because we blew shit up and they were there. Their spectra hadn't been measured before, and then we went and looked for them, and lo and behold, they're in space, which is super cool.
That is incredible. One last question from someone in the audience was asking, is there any books that you found particularly inspiring in this field, or that you find useful for someone wanting to learn more about this entire field or topic?
So I don't know of very many books that are written for a general audience, although I have one here. on my coffee table. Let me pull it out here. And I believe it is called Molecules, the Elements and the Architecture of Everything by Theodore Gray. Make sure I have the right one. In that book, he actually goes through, I think, a number of different molecules that are found in space, as well as a bunch of molecules that are found here on Earth, and that's pretty cool. From a technical standpoint, the sort of go-to is the physics and chemistry of the interstellar medium by a guy by the name of Xander, Xander Thielens, Tielens, off the top of my head. He's one of the sort of founders of the field of astrochemistry, and it's a really fantastic book. But it is written for a technical audience. It's sort of the first year graduate student level in astronomy or physics.
Excuse
Those
me,
two
what
sounding
can you
incredible.
repeat the sex? Sorry, Jamie.
I'm just going to thank you for answering my questions, and thank you for the book recommendations. They sound great.
I was just
Yeah,
trying to write
you,
them in the room chat. So I got the first one, and the
yeah.
second one is the physics
The
and
second one is
right
the physics and
and
chemistry of the interstellar medium.
oh, thank you.
Mm-hmm.
Great.
And the last name is Thielens, Tielens.
Well, thank you so much for this amazing talk. And I have one last question because everyone asked wonderful questions and you gave such a great presentation. And this one's relatively silly, probably. We had like a science update newsroom last week, and we listened to how black hole sounds, and it sounded like despair. Is there a sound cloud for these clouds where you look at?
That's a cool question. So I don't know that anyone has done an audio sort of transformation for molecules specifically. However, I do know that one of the radio telescopes that I use, the Atacama Large Millimeter Array, ALMA, ALMA, it's a array of 60 some odd radio antennas in the Atacama Desert in Chile. They did a big thing, I think a year or two ago, where they did transform a bunch of the signals, the radio signals from their telescope into audio frequencies so that they could be listened to. I would find it hard to imagine that anybody, none of the spectra that they transformed were lacking molecules, because that telescope sees a lot of molecules. So if you Google ALMA and then look for sounds of space or something off of that, you can probably find that project. I'm blanking on the name off the top of my head, but it's probably the closest that you're going to find, would be my guess.
Wonderful. We are looking for, some opposite sounds because it sounded really
Sure.
horrific.
Understood.
It
Yeah.
really sounded like despair. I'm just interested to know if a birthplace of stars maybe sounds quite differently. It would be very cool to know. So thank you
Sure.
for
Yeah.
going there.
Hi, breaking. May I, let me squeeze in with a quick reference question.
Sure.
Earlier you mentioned the smiley. Dennis asked the question there on the machine learning part. So you mentioned the researcher and Intel. Could you repeat the name again? I found that's very interesting. I want to follow it up.
Sure.
I missed
So
it.
my postdoc's name that did all of that work, and it was all him. It's over my head. He's the genius here. His name is kin, K-I-N, long, L-O-N-G, Kelvin, like the unit or the Lord, however you want to work it. And then his last name is Lee, L-E-E. So Kin Long Kelvin Lee. And he's the first author on that paper entitled Machine Learning of Chemical Inventories. It's in the Astrophysical Journal, and it should be open access at this point, because the Astrophysical Journal, I think, is now entirely open access.
Great, thank you.
You got it.
Well, thank you so much for your time, and it's 10:30 now, p.m. EST. So, yeah, I really appreciate all the questions you answered and your amazing talk. And please come back if you have updates on your work, or if you want to share something, another project maybe. Feel free to always come back here. And yeah, thank you everyone for coming and asking great questions and being part of this room here, and for all the questions in the chat. And yeah, I hope to hear everyone at some point soon again, especially you, Brett. Thank you.
Absolutely. Thanks for having me. This is an absolute blast. As I said, feel free to reach out to me online, get in contact if you have other questions. And this is fantastic. Have a great rest of your evening or day, depending on where you are, everybody. Take care.
You
Yeah,
too.
thank you,
Thank you
Brett.
very much.
Thank
Great
you.
talk.
Thank you so much. Come on back anytime.
Thanks. Have a good night. Bye, everybody.
Bye.
Bye. Yeah, and we'll have our next room on Friday. We don't have a room tomorrow. We had 2 rooms today. Um, so if you like guest speaker events like this is your club, follow it. And we'll have on Friday at 9:30 a.m. EST a guest speaker from the UK, and he works on saving the honeybees. Honeybees are dying from different diseases, and he published his work where he developed a varroa-resistant honeybee. So yeah, come back. It will be really interesting. He's a really wonderful scientist and person. So I think it will be a really entertaining room. And then on Friday afternoon, we'll have here, led by two of our club members, Krishna and Faris. Faris is a scientific journal editor, and they will give people tips about how to write a scientific article if you're interested. It will go around 1 hour, and yeah, if people are interested and like rooms like this, we'll maybe make a follow-up room on how to write grants, to get grants approved. So yeah, feel free to come back on Friday, and then we'll come up with a round table, more discussion type of room on Saturday. So thanks everyone for coming. Enjoy the rest of your evening or morning or wherever you are, in the middle of the night like Jamie. Sleep well.
And sleep.
Thank you, everybody. Have a good day.
Have a
Have
good night.
Thanks, everyone.
Bye.
Thank
3,
you.
2, 1. Bye everyone.